Unit 8, Video Lecture 2, Mole-to-Mole Reactions. Remember that stoichiometry is the study of the relationships between the amount of reactants and the amount of products. So since we're talking about amounts, we're going to use the SI unit for amounts, which is the mole. So we're going to use the mole map that we started working and expand it. We already know that we can go from the mass of a known substance to the moles of a known substance by using molar mass. And we know that we can go from the particles of a known substance to the moles of a known substance by using Avogadro's number. What we can also do is go from moles of a known substance to moles of an unknown substance, and to use this, we're going to use our mole ratio that we practiced finding in our last video lecture. So, how many moles of N2O and H2O are produced from 2.25 moles of NH4NO3? Well, we're given our 2.25 moles of NH4NO3. We want two things. First, we want the moles of N2O, and then we want the moles of H2O. So to do this, we'll go from moles of one substance to moles of our new substance, and to do that, we'll use our mole ratio. So first, we'll take our 2.25 moles of NH4NO3, and from our balanced equation, we see that there's 1 mole of NH4NO3. Let's move this over a little bit. So from our balanced equation, we see that there's 1 mole of NH4NO3, and our first want, our NO2, there's 1 mole of N2O. So moles of NH4NO3 cancel out. We're left with moles of N2O. So 2.25 times 1 divided by 1 is 2.25 moles of N2O. Notice I have 3 things. I have a number, I have my unit, and I have my substance. All 3 of these things are going to be important and are going to be needed when you report your answers. So now if I'm going to look at my second want, I want moles of H2O. So I'll still start off the same way. 2.25 moles of NH4NO3. I still have 1 mole of NH4NO3. But now I have 2 moles of water. So I take my 2.25 times 2, and I get 4.5 moles of H2O. The one thing I have to be careful about is that in my given, I'm given 3 significant figures. Well, 2.25 has 3 significant figures, but 4.5 only has 2 significant figures. So I need to include a trailing 0 in order to get that third significant figure. So let's look. How many moles of HCl are needed to react with 2.3 moles of zinc? Well, we're given 2.3 moles of zinc, and we want moles of HCl. And so our map is moles of zinc to moles of HCl. And I do this by using my mole ratio. So 2.3 moles of zinc. I have 1 mole of zinc in my balanced equation. And the coefficient 2 in front of HCl tells me I have 2 moles of HCl. Moles of zinc cancel out. I'm left with moles of HCl, so it's 2.3 times 2, or 4.6 moles of HCl. And I check, I have 2 significant figures here, and 2 significant figures here. So I take my C2H2, and it's a combustion reaction. So C2H2 plus O2 yields CO2 plus H2O. There's my skeleton. Now to balance this, I have 2 carbons, 2 hydrogens, and 2 oxygens, 1 carbon, 2 hydrogens, and 3 oxygens. So I balance carbon by putting a 2, but that changes my oxygen. Now I have 2 times 2 plus 1, so I have 5 oxygens on the product side. Well, in order to get 5 oxygens, I need some number times 2 to give me 5. So X is going to be 2.5. Well, remember that I can't have 2.5 molecules of oxygen. I can't have that 0.5, so what I'm going to do is, just like I did with empirical formula, so I'll multiply all of my coefficients by 2. So I multiply everything by 2, and my balanced equation is 2CH2, 5O2, 4 CO2s, and 2 H2Os. So I'm given 5 moles of C2H2. I want my moles of CO2. So I go my moles of C2H2 to my moles of CO2, and to do that I'll use my mole ratio. So 5 moles of C2H2. The 2 tells me that there's 2 moles of C2H2 and 4 moles of CO2. Moles of C2H2 cancel out, so it's 5 times 4 divided by 2, or 10 moles of CO2. The last thing for me to do is to check my significant figures. 5 has 1 significant figure, and 10 also has 1 significant figure. Remember, that is a trailing 0 without a decimal. So 10 moles of CO2 is correct. Pause the video lecture here and practice on your own. If you need to see how these were worked out, stay tuned. Otherwise, you can stop the video lecture and start practicing. Don't forget to fill out your reflections. Magnesium burns an oxygen to produce magnesium oxide. How many moles of oxygen are needed? So we have 0.52 moles of magnesium. We want moles of oxygen. So we're going to go from moles of magnesium to moles of oxygen, and to do that we're going to use our mole ratio. So, in order to use our mole ratio, we're going to need our balanced equation. So, magnesium reacts with oxygen to produce magnesium oxide. Remember, for magnesium oxide, magnesium is a +2, oxide is a -2. So we crisscross, drop our signs, and reduce, and we have MgO. Now to balance, We have 1 magnesium on the left, 1 magnesium on the right, 2 oxygens on the left, 1 on the right. So we put a 2 in front of MgO, and it changes magnesium and oxygen. Oxygen's balanced though. And a 2 in front of magnesium, now we have 2, 2, 2, 2. So we take our 0.52 moles of magnesium, and from our balanced equation we have 2 moles of magnesium in the reactants, and we only need 1 mole of oxygen. So 0.52 divided by 2 gives me 0.26 moles of oxygen. In this problem, we're given 0.75 moles of silver nitrate. We want moles of aluminum nitrate. So we'll go from moles of silver nitrate to moles of aluminum nitrate. And to do that, we'll use our mole ratio. So 0.75 moles of silver nitrate. From the balanced equation, I see that I have 3 moles of silver nitrate, and I have 1 mole of aluminum nitrate. Moles of silver nitrate cancel out. I'm left with moles of aluminum nitrate, which is what I want. So it's 0.75 divided by 3, and I get 0.25 moles of AlNO3.